I I welcome you all for today's talk, and we are very fortunate to have Professor Liang Wang. Probably the topmost researcher in biomedical engineering, and it's a great honor to have him here. And little bit about Professor Liang Wang. He's a Bren Professor of Medical Engineering and Electrical Engineering. Andrew and Peggy Chern Medical Engineering Leadership Chair and Executive Officer of Medical Engineering. Right now he's a professor at Caltech. And a little bit about his background. He did his bachelor's at Hangzhou University of Science and Technology in 1984, followed by his PhD at Rice University. And currently he is a Bren Professor at Caltech. His research interest is wide. I'll just mention some of them. Photoacoustic tomography, and that includes microscopy and computed tomography. Thermoacoustic tomography, light speed compressed ultrafast photography, time reversal optics, wave shaping, and quantum imaging and physics. So there's a long list. Probably it will take more time. I will just say that we are very fortunate to have him, and we'll just ask Professor Liang to take over and deliver the talk that we're looking for so long. Professor Liang, please take over.
Thank you, Professor Mandel, for inviting me to speak here. Today, I'll be talking about an emerging technology called photoacoustic tomography. It's a technology that allows us to image from subcellular organelles to patients and provide molecular absorption contrast. Now, why do we want to work on optical imaging to begin with? Light is very special because light-matter interaction takes place at a molecular level. Given the importance of molecules in biomedicine, we really have to work on optical imaging, despite all the challenges. By detecting molecules, we provide in vivo functional imaging, analogous to functional MRI, in vivo metabolic imaging, similar to PET, in vivo molecular imaging of gene expressions or disease markers, in vivo label-free histologic imaging. The biggest challenge we face for optical imaging is penetration, because light scatters a lot in biological tissue. Within a millimeter of depth, photon propagation transitions from the ballistic regime into the diffusive regime. Conventional microscopy allows us to see subcellular organelles, but only provides a penetration up to 100 microns at the so-called aberration limit. We stagnated at this limit for hundreds of years until modern light sources were invented, which allowed us to provide 10 times deeper penetration up to 1 millimeter at the so-called optical diffusion limit. Using photoacoustic tomography, we advanced the penetration by 2 more orders of magnitude. Now we're talking about multiple centimeters penetration, providing whole body small animal imaging or human organ level imaging. We do face the next challenge, the so-called optical dissipation limit. We don't really have a technology yet to overcome the next limit. In photoacoustics, we start with a short laser pulse, typically nanosecond pulse width, but we broaden the laser beam such that energy per area is within the NC safety limit. So this technology is very safe. You're not going to get a laser damage using the technology properly. We allow photons to scatter around in biological tissue to provide deep penetration. When light gets absorbed, it generates rapid heating. Every millidegree gives us 800 pascals of pressure, which is detectable already. Within the safety limit, we can generate hundreds of millidegrees. Therefore, we have a good signal-to-noise ratio to work with. Outside the tissue, we receive the photoacoustic signal as opposed to the return light, because acoustic scattering in biological tissue is orders of magnitude weaker than optical scattering. tissue is essentially transparent to ultrasound. As a result, we can form a very sharp image using acoustic signals. However, we retrieve optical contrast. We're combining optical contrast and ultrasonic resolution in the same modality. We can use the simplest analogy to explain the principle of this imaging modality. If you have a thunderbolt, when you see the lightning, you can reset your stopwatch to time 0. When you hear the thunder, you record a time delay T1, multiplying T1 by the speed of sound, you will get a radius for a spherical shell on which lightning took place. If we have 3 such measurements, we would pinpoint the thunderbolt. However, in a real piece of tissue, we have a volumetric source that's heterogeneous. So we don't have a single point source. As a result, we need far more than 3 detectors to form an image. Oftentimes, we use hundreds, if not thousands, of detectors. There's something called inverse spherical Radon transformation that allows us to back project the data received, acoustic pressure data, into the tissue space to form an image. In the forward problem, if we illuminate an object with a broadened laser beam, at time t, we essentially integrate all the initial pressure on this spherical shell, which is called the spherical Radon transform. Radon never inverted this problem, so our field had to work on this problem. Now, this problem turned out to be invertible. So P is the raw data. That's the pressure received at detector position R0 versus time t. P0 is the initial pressure induced by the laser, and that actually relates to the optical contrast. So this provides the image. P0 provides the image. We use the solid angle to unify different detection geometries. We have to time delay the signal back into the tissue space. If we simply integrate the raw data pressure after time delay, we are essentially using the ultrasound beamforming. If we incorporate the high frequency filtering effect, we get an exact solution. So this is a closed form analytical solution. In 2003, we acquired the first functional, also the first in vivo photoacoustic tomographic images in small animals with an intact scalp and skull. This is very similar to functional MRI. We can see one-sided brain stimulation by wiggling the whiskers of a small animal. This paper now is one of the most cited papers in our field. In fact, this paper kicked off the growth of our field, as you can see this plot. Since 2010, the Conference on Photoacoustics has become the largest at Photonics West, which has 20,000 attendees each year. Our field has published in each year more than 1,000 peer-reviewed papers. So this is a very robust field now. Photoacoustic technology has been commercialized by more than 20 companies. 3 of them have received regulatory approval for clinical use. A unique ability of photoacoustic tomography is the multi-scale imaging capability with consistent optical contrast. This plot shows the imaging depth versus the spatial resolution. Photoacoustics allows us to image from organelle level all the way to small animal organism or human organ level with the same optical contrast. This dashed line connects all the different implementations. No matter what depth we work at, we can provide about 200 pixels in the depth direction. Therefore, we provide high quality images. This type of multi-scale imaging capability is expected to enable omniscale biological research from organelles to organisms, and accelerate translation of microscopic lab discoveries to macroscopic clinical practice. For the O3 work, we used a single element transducer, which took a long time to acquire image. Here, we use a single impulse and we achieved panoramic photoacoustic CT. The system can be configured for truncal imaging. We start with a laser. The laser beam is converted through a conical lens into a hollow cone beam for maximal energy delivery efficiency. We use a full ring ultrasonic transducer to receive signals all around the small animal for the best view. We follow the spatial Nyquist sampling criterion, namely 512 channels, to minimize any aliasing artifacts. We use preamplifiers immediately to amplify the signal to overcome any subsequent cable noise to maximize the signal-to-noise ratio. We use a one-to-one data acquisition for single-shot imaging. Therefore, for a cross-sectional image, the data is acquired within acoustic transit time across this whole body of a small animal. For a small animal, we're talking about tens of microseconds. So we are providing sonic speed imaging using this device with a single laser shot. We use the computer to reconstruct image and display the outcome. Here's a close-up. We can see the hollow cone beam. The ultrasonic focus in the elevational direction provide the Z resolution. The XY resolutions are provided through the inverse spherical Radon transformation. The system can be reconfigured for brain imaging. Here we use a diffuser to form a solid cone beam for maximal energy delivery efficiency. And the rest of the system is very much the same for operation. This movie shows how quickly we can acquire cross-sectional images, and then we repeat our laser pulse at 50 Hertz. Therefore, we can provide 50 Hertz frame rate. The red line shows the current cross-section being imaged. We're scanning along the trunk of this small animal. You can see details of the whole body of the small animal, as shown in the close-up as well for different organs. You can imagine there are many types of applications of this kind of imaging capability. For example, for drug discovery, where you don't have to use ionizing radiation, you don't even have to use contrast agents. So we can monitor the same animal over many months without worrying about radiation dose, which might kill the animal. This technology has been licensed to 2 companies. In fact, they've perfected the technology. They have surpassed our lab's image quality, as you can see from here. Then we scaled up our system for human level imaging. This is a breast imaging system. We call this single breath hold panoramic photoacoustic CT. It's designed for human breasts. We scaled up the system. This is a 22 centimeter diameter ring array, which is big enough to accommodate most breasts. We use 1064 nanometer laser light. We broaden the laser beam to illuminate the breast. We only slightly deform the breast against the chest wall, which is painless. Such slight compression allows us to minimize the light penetration requirement, allows us to stabilize the breast to minimize any motion-related artifacts. The rest of the system is very similar to the small animal imaging system. With a single laser shot, we get a 2D cross-sectional image within 150 microseconds. So there's no motion artifact to worry about. Again, this is sonic speed imaging within the acoustic field of view. Within a single breath hold, we can acquire a 3D image, which is within 15 seconds. The smallest image blood vessel diameter is 1/4 millimeter. We can provide 4 centimeter one-way penetration with a single laser shot. In this example, the breast is radiographically dense. X-ray mammography missed the tumor. Ultrasound actually found the tumor. We placed a metal target on the breast surface. Then we took a second mammogram. Using our technology, we can see the breast tumor right here, as indicated by the double arrows. Presumably due to enhanced angiogenesis, which shows more blood vessels. So the vessel density is greater in the tumor region. We can track the breast at very high imaging rate. As a result, we can analyze the motion to figure out a stream map. So this is essentially elastography. We can see the breast tumor region is different than the surrounding normal region. Here we compare our technology with the commercially available US FDA approved clinical system. The left side is from the clinical system. It's shown to provide greater specificity for cancer diagnosis. The middle one is from our device. We can show far greater details of breast blood vessels, as you can see right here. Using the same human subject, we also acquired gadolinium-enhanced MRI images. Now, the numbered arrows indicate blood vessels that are imaged by both photoacoustics and MRI. The lettered arrows indicate vessels that are imaged by photoacoustics but missed by MRI. Photoacoustic imaging requires no injection of any contrast agent, where MRI requires injection of gadolinium. So presumably, in this particular case, photoacoustics has shown greater sensitivity, greater details in blood vessel imaging. We're showing the feeding vessels to this tumor right here. Then we built another system that provides isotropic spatial resolution. So instead of using a ring detection geometry, we're using a hemispherical detection geometry. There are 4 arcs of ultrasound transducers. We can rotate the 4 arcs to form a hemispherical surface. The system operates in 2 different modes. In an atomic mode, it requires 10 seconds to form a higher resolution 3D image. For functional mode, it takes only 2 seconds to form an image. The system provides 2 different laser wavelengths to target both oxyhemoglobin and deoxyhemoglobin. Here, fingers are hemiclean patient. With the finger tapping, we can see the brain activation. This plot shows the greater detail of the signal variation. On the next slide, I'll let our neurosurgeon clinical collaborator, Dr. Ruffin, explain the comparison with the 7 Tesla MRI.
Here we present results from subject 1, 7T MRI on the left, functional pact on the right. Individual functions are flashed in, starting with finger tapping, lip puckering, tongue tapping, passive listening, and silent word generation. Vessels for co-registration are then labeled 1 through 4, vessel 1 and 2 being superficial temporal artery, 3 and 4 being cortical arteries. The images are overlaid, and then individual functions are flashed in, starting with finger tapping, lip puckering, tongue tapping, passive listening, and silent word generation. The vessels are again pointed out individually, vessel 1 and 2 being branches of the superficial temporal artery, 3 and 4 being cortical vessels. The lateral perturbations allow for visual spatial appreciation of the co-registration. The images are then separated, and native T1 masks are faded in. Again, 7T MRI on the left, functional packed on the right. Individual functions are then flashed in, starting with finger tapping, axial, and coronal images through the area of interest are introduced below. Next, lip puckering, tongue tapping, passive listening, and silent word generation.
We can also make our probe handheld. In this particular application, we're targeting in vivo photoacoustic CT of the central lymph node. We first inject organic dye, which is FDA approved, into the breast. The dye will follow the lymphatics and accumulate at the central lymph node. Then we can image the central lymph node using the optical contrast from the dye. Then we can sample the central lymph node using photoacoustic guidance. So we take cells out of the central lymph node. Then we can examine the specimens for cancer. So we can make this procedure minimally invasive instead of open surgery. And you can see this result in a real patient. You can see the needle right here. You can see the central lymph node. The handheld probe can also be used to examine the oxygen consumption in the brain. The current tool is invasive, and we like to make this non-invasive. As we know, the carotid artery provides oxygen to our blood. That's the input to the brain. And the output is the jugular vein. We can image the oxygen saturation of both the carotid artery and the jugular vein. So far, our result meets the expected value. And so this can potentially provide a non-invasive tool for monitoring of oxygen consumption, especially during surgery. We can also image circulating tumor cells. As we know, the primary tumor may not kill the patient. It's oftentimes the metastasis that kills the patient. Circulating tumor cells are the major channel for metastasis. Currently, there's no non-invasive tool that allows us to image circulating tumor cells. Photoacoustics has been demonstrated to image melanoma circulating tumor cells, which have enhanced melanin concentration, thus providing high optical contrast. In this particular patient, you can see in this blood vessel, we imaged in vivo, a bright dot was captured to fly across the field of view. In this video, you can see that a doublet traveled across the field of view as well. You can imagine all sorts of applications using this type of capability. Our field had concluded that it was not possible for photoacoustics to image flow beyond 1 millimeter in depth, but we have proven our field around so that it turned out even beyond 1 millimeter, we can still image flow as shown in the videos here. In this particular demonstration, we're looking at mainly venous blood. So venous blood has enough physiological heterogeneities for us to image using photoacoustics. We can scale our imaging resolution to the microscopic level. This photograph shows the first 3D photoacoustic microscope. The papers shown here are also one of the most cited papers in our field. The close-up shows the key parts of the technology. We have this cone beam that's focused into the tissue. On the tissue surface, we have a donut shape. the core of the beam was made dark to minimize surface interference. We use confocal detection to receive the photoacoustic signal. With a single laser shot, we get a time resolved or depth resolved image because of the acoustic time of arrival. And then we can raster scan to get a 3D image. Now we can also achieve optical resolution. Within the top 1 millimeter of depth, we can focus light. Therefore, the X-ray resolution is defined by the optical focus. Now, sometimes if we were to use a Gaussian beam, the depth of focus is quite limited. We can use a needle-shaped beam to extend the depth of focus. In certain cases, we can see the advantages between the Gaussian beam and the needle beam. Certain areas that were out of focus can be brought to focus. There are more examples. We know that pathology is still the gold standard for disease diagnosis, but sometimes it takes a long time to diagnose specimens. For example, the HE staining for bones can take up to 7 days. Using photoacoustics, we provide decalcification-free and label-free imaging, and we can provide histology equivalent images. And we can provide the imaging within 11 minutes at the current rate, and this is not even the ultimate limit. Studies have shown that if we have a reliable intraoperative diagnostic tool for bone surgery, we can reduce the margin from 20 to 2 millimeters. So that's a factor of 10 in reduction in linear dimension. By volume, you're talking about up to 3 orders of magnitude in bone volume, because bones are so hard to regrow. It's very important to conserve healthy bone. We can also improve the resolution beyond the optical diffraction limit using nonlinear photoacoustics. The left image shows the diffraction limited resolution at 234 nanometers. And the middle one is 90 nanometer resolution based on nonlinear photoacoustics. We call this photoacoustic nanoscopy or super resolution imaging. You can compare the two images. We're imaging an organelle, which is a subcellular structure. This is the mitochondria. And the right one is an EM micrograph. Now, photoacoustics still has somewhat limited penetration. We're not able to provide whole body human imaging yet. So we're exploring pure ultrasound, and more importantly, we plan to explore the RF or microwave regime of the EM spectrum, which can provide deeper penetration. For now, we've demonstrated the first whole body human ultrasound CT system. You can see the system in operation. We have a 60 centimeter diameter system, which is big enough to accommodate most human trunks. We have 512 element ultrasound array for signal receiving. This slide shows the first whole body human ultrasound CT images. You can see some of the internal organs quite well using our initial system already. So far, we're talking about sonic speed imaging. Would it be possible to provide light speed imaging? So let me touch upon another technology our lab has been working on, which is called compressed ultrafast photography. The first version achieved 100 billion frames per second. At this rate, we were able to see a light pulse in action in real time. It was not possible for any other technology to see a light pulse at light speed. We can see this light pulse getting refracted. Here, two light pulses are having a race. We can also reconfigure our system for a two-colored version. The green channel shows the excitation pulse. The red channel shows the fluorescence decay. So this is a single shot fluorescence lifetime imaging. We can see the entire event with a single laser pulse. We can use our technology to study physics. We know that when the sound source propagates above the sound speed, you have the supersonic Mach. This is a sonic boom. This was captured by NASA. Now there's an optical counterpart that was not possible to capture before. We call this optical boom or superluminal Mach. So we created a tunnel where light propagates at the speed of light in air, but that tunnel is surrounded by some other material, so light propagates at a lower speed. And therefore, we create a superluminal situation that creates this optical boom or superluminal Mach that was captured with a single light pulse. We can also target some of the biological problems. Here, we're trying to image electrical pulse propagation along myelinated axons. Between the two adjacent nodes of NVA, you have very high speed propagation of electrical signals, and that was not possible to capture. Here, we can use our technology to capture the propagation as shown right here. We use the phase contrast to detect this type of signal. So we don't actually use labeling. Now, this is just a demonstration of this capability. If we can image the signal propagation in a neural network, we might be able to tease out what type of propagation corresponds to what type of brain function. We've increased our speed even further to 219 trillion frames per second. And so this plot shows the sequence depth or the number of frames versus the imaging depth. You can see that the compressed ultrafast photography or CUP family sits at the preferred location in terms of both speed and the number of frames per movie that can be provided. So the YouTube videos on Caltech's light-speed camera has been viewed over 60 million times. So if you Google Caltech light-speed camera, you will find the YouTube videos. So far, everything I talked about is classical. Can we leverage quantum resources to provide quantum imaging that could be super resolution? There are two types of limits. One is called a standard quantum limit. In this limit, the spatial resolution scales with 1/√n. The standard quantum limit is achieved with a regular light source, such as a laser. Examples include two-photon microscopy or super-resolution imaging, such as PALM or STORM. In two-photon microscopy, you pump the molecule to a virtual state using one photon, but within the lifetime of this virtual state, the second photon has to follow to excite the molecule to the excited state. Intuitively, n statistically independent photons average the spatial standard error down by √n, or by √n times, according to the central limit theorem. Now, the spatial resolution at the Heisenberg limit scales with 1/n, so this is a more efficient scaling. The Heisenberg limit is achieved with an entangled photon source, such as SPDC source, spontaneous parametric down conversion. Intuitively, in entangled photons, behave like one with n times greater momentum or shorter wavelength. In this demonstration or illustration, we got entangled photon pairs. One arm goes through the object arm, so the object is placed only in one arm, and the other arm is the reference arm. Oftentimes we call this the idler arm, but we use coincidence counts to provide imaging signal. This allows us to achieve the Heisenberg limit. This was demonstrated in biological cells using entangled photon pairs. You can see the quantum image provides better resolution than the classical image acquired using the same system. Just to come back and summarize what is important in photoacoustic tomography. We provide rich optical contrast and multi-scale imaging from organelles all the way to patients. There are diverse molecules that can be imaged using light. All sorts of biomolecules, including nucleic acids, carbohydrates, lipids, proteins, other endogenous molecules. Exogenous contrast can be imaged as well, such as dyes and nanoparticles. We can provide in vivo functional imaging. We can image oxygen saturation, perfusion, brain activity, because we can image the concentration of hemoglobin, the oxygen saturation of hemoglobin, and blood flow. We can provide in vivo metabolic imaging. For example, we can image the metabolic rate of oxygen. We can provide in vivo molecular imaging of different biomarkers, such as integrin, VEGF, HER2. We can image reporter genes. We can even provide in vivo label-free histologic imaging. Finally, let me thank Caltech for building me a dream lab. This photograph shows one of the floors of our lab. We have openings for graduate students and postdocs. Credit goes to lab members. We're mainly funded by NIH, but we also have funding from NSF and CZI. There are a couple of books if you're interested in more details. Thank you very much.
Thanks a lot, Professor Wang. What can I say? What we have witnessed now, I would say, is the future of biomedical science. And this is the direction it's going to go. A great talk and great insight. I mean, a lot of learning for us. And what I've seen today is some of the wonderful volume images. I have not seen them before. Thanks a lot for enlightening us. And this talk is going to be available for on YouTube forever, so that people can actually learn from it and also go through it. We have also parallel sessions going on in ISAT Trivandrum. So I want to know if there are some questions that anyone wants to ask from ISAT as well as from the present session. Yeah, we have Professor Wang, one question from one of our faculties. Yeah, please go.
Sure, please. I do see a question in the chat box. Can I answer that question first?
Yes, Professor.
Yeah, so the question is, there will be photo bleaching in fluorescence microscopy. Will there be any similar effect in photoacoustic imaging? So fluorescence is easy to bleach, as we know, and absorption usually is harder to bleach, especially when we image blood, red blood cells. So we don't really use very strong light, and the blood is always circulating, and so we don't really have this bleaching problem. And also, even when you have a fixed sample, if you image in the same place, in theory, even when the molecule is bleached, you can potentially tune the laser wavelength and find a different band, and you might be able to see the molecules again. But usually we don't encounter the same problem. And so that's the beauty of absorption. With the fluorescence, as we know, you have to get a sufficiently high fluorescence quantum yield in order to see fluorescence signals. But for absorption, you don't have the same issue. In fact, 1 minus the fluorescence quantum yield provides the absorption signal. And oftentimes, your fluorescence quantum yield is not very high. Even in a good situation, you may have on the order of 10% of fluorescence quantum yield. And so a majority of the signal actually goes to the absorption channel, which provides photoacoustic signals. Now, if the molecule is bleached, it's usually pretty hard to find another wavelength that gives you still fluorescence, because the fluorescence quantum yield may not be there. But the molecule is always absorbing at some wavelength. You need to tune the laser wavelength. And so this could be a solution to the bleaching problem. And so essentially all fluorescent molecules can be imaged by photoacoustics. It's the same excitation wavelength. You split the signal between fluorescence and photoacoustics.
Thank you, Professor Wang.
Sure.
There is a little bit of internet issue, but I would like to continue asking one of my questions.
Sure.
That's like, what is the best resolution and depth that PAT can provide in a moving target, such as heart or lungs, when it is actually functioning? So that is something,
Right.
if you can, yeah.
Right. So the photoacoustic imaging can be done using single laser shot. So theoretically, it can be really fast. Like the single rain I showed, for a 2D cross-sectional image, within 150 microseconds, you can get a 2D image. So the motion is not a problem. However, if you got a ring detection geometry, you can only get a 2D image. And so the ideal detection geometry is a densely packed. In fact, I didn't have time to show. We just built a densely packed hemispherical surface. So with a single shot, we get a 3D image. And so that's also within the acoustic transit time, roughly 150 microseconds on that scale. And so you can avoid motion artifact. So for motion is not a challenge, because photoacoustics is a single shot sonic speed imaging. Now, heart and lung are not necessarily the easy organs to image, because the heart is actually behind rib cage. And so bones can potentially block or scatter ultrasound signal or attenuate ultrasound signal. And so for ultrasound imaging of the heart, we actually find a window between the rib bones. And so that allows us to see the heart. Or we can use transesophageal endoscopes to see the heart. And so that becomes minimally invasive. The lung is even harder, because the lung is filled with alveoli. So that's kind of ultrasound scattering, attenuates ultrasound a lot. And so photoacoustics has not been widely used for lung imaging. But in terms of motion per se, photoacoustics is capable of imaging in real time at a reasonably high frame rate. And the technology has not even reached the limit yet.
Dr. Jayaprakash has one more question to ask.
Sure, sure.
So another question I had is this quantum imaging, right? You're doing with entangled photons.
Mhm.
So my question was, currently you're doing at microscopic scale.
Mhm.
Can this, what is your take on whether quantum imaging can be used to go beyond 10 centimeters? Will that be possible, or will you have some issues there? Because the entanglement, people have shown that you can have long distance communication, atmospheric turbulence, and these kind of situations, right? So the question is whether our scattering media also can be overcome.
It's a very interesting question. Entanglement, the question is whether entanglement can survive scattering, in real thick tissue. So right now we're using very thin samples. We're just trying to demonstrate super resolution. Can we actually potentially use entanglement to provide super depth, if you will? That we toyed with that idea, but so far we haven't been able to demonstrate, so partly because the sources are kind of weak, because the SPDC process is terribly inefficient, so the efficiency is like 1 per million in terms of conversion from the pump photons to the down converted photons. So when the light sources, the entangled light sources are so dim, we have to live with what we have. The hope is that down the road, if we can figure out ways to make the sources brighter, or there is an effort, group of scientists in Taiwan, they made many parallel sources that provide entanglement. And so equivalently, they made the source much brighter. And so that's kind of the future, because each source might be really dim, but if I got 1 million of them and I got 1 million detectors, all of them are working in parallel, then there might be something exciting coming out of it. So right now the quantum imaging, I have to say, is more like demonstration of feasibility. It's pretty far from practical use. And deeper penetration is even more exciting if we can get there. So we need to keep that idea in mind and see, hopefully one day we can show if that's a possibility.
Yeah, sorry, Professor Yang, we have one more question online, so I'll just read it off.
Sure.
What is the penetration depth we can use in brain imaging, and is there any chance that sound get reflected from the bone and tissue interface?
Yes, actually, so the bone has attenuation, reflection, and some scattering. And so bone actually distorts our images. And we do get signals coming through the bone. And so light can go through the bone, reach the brain cortex, and then the sound signal can come out. So we've demonstrated the signals are there. And we're still working very hard on de-aberration to sharpen the images. And so it is a very challenging problem the field faces. In terms of depth, right now we've demonstrated cortical level imaging. And so it's a few centimeters, below the skull, you can reach the brain cortex. But a lot of the functional activities actually take place at a cortical level. And so it's a good match. If you look at both MR images, a lot of them actually show the functions at a cortical level. And so that's why photoacoustics has a future.
Yeah, thank you, Professor Wang. We are happy to see that how biomedical science is being pushed in your lab. And, thanks a lot for enlightening us. So once again,
Thank you all very much.
Yeah, thank you, Professor Wang. Thanks a lot. Yeah.
All right. Okay, bye.
Right.